very much. And I would like to thank the organizer for inviting me here. And I'm very happy to be in Paris, a very amazing city and country. And also, it's very amazing to be surrounded by so many great names. Curie, Poincaré, and Fourier. Just so many great names. I just like it. And today I'm going to talk about the quantum learning control. And my name is Rebing. Just for you to memorize my name, I just explain a little bit of my name in Chinese. So my Chinese name consists of 3 Chinese characters. Rei means heart, and Bing means eyes. So literally, I'm just kind of the hot and cold duality, just like the particle wave duality in quantum mechanics. Okay, so just, I want to introduce my collaborators. So I think many people should know Henri, who did a lot of great work in quantum control. And these 2 people they actually are not in the domain of quantum control. They come from the classical continuous engineering, and they are experts on the so-called iterative learning control for classical systems. And the reason I collaborate with them is that I found that although we have a lot of ideas on learning control for quantum mechanical systems, but some very smart ideas in classical iterative learning control have not been applied for quantum control. So I just want to discuss with them and find some new way to improve the performance of the quantum control using learning. So, and if you have interest, I recommend you to a very good book written by Professor David Owens from the University of Sheffield. And many of them very good ideas in classical learning control can be found here. And firstly, I'm going to talk about some ideas in quantum control, quantum learning control. And then I use 2 examples showing how you can use the iterative learning to improve some very standard algorithm for optimizing quantum control. One is deconvolution for calibrating the control pulses, which is often used in microwave control. And also GRAPE. I think everybody knows GRAPE. And the traditional GRAPE is a offline fashion, open loop. But if you combine the GRAPE with the data to change it into the online fashion, I propose the so-called d-GRAPE algorithm using a data-driven model for GRAPE. And finally, the conclusion and perspectives will be given. So firstly, I think when we talk about the quantum learning control, I think the earliest application of learning control was in chemical reactions. So when you want to use a laser pulse to control a chemical reaction, you just shape the laser. So usually because the laser pulse is just so fast, you cannot shape the laser pulse in time domain. But you can do it in the frequency domain. Basically, you can generate a standard Gaussian pulse and split it into a different frequency component. And you can change each frequency component by the phase and amplitude, and recombine them, then you can shape the pulses. Okay. If you have the ability of shaping the pulse, then you can apply the laser pulse to a chemical reaction, a system. For example, this is a very famous learning control. If you have the learning control of the reaction, you can selectively excite the high harmonic generation. Over here, high harmonic generation. You can selectively excite the 27th order high harmonics. So actually, the earliest idea of learning control was proposed in 1992. Actually, before that, optimal control theory has been introduced to optimizing quantum dynamics. But the idea is that based on the Schrödinger equation, you have to optimize the control, you have to know the Schrödinger equation. You have to know the model. But the problem in chemical systems is that the model is too complicated. Sometimes you can never get the model, or even if you have the model, but the model is too complicated, you have no way to compute it. So Henri proposed that, okay, let's forget the model. Let's just look at the data. Let's shot the laser to the system and just observe the output. And you use some genetic algorithm on the computer to adjust your laser pulses. Then you do this again and again. Because in chemistry lab, you can do this experiment very fast. You can do even, like, you can For example, you can do even like 100 or 1,000 times of the experiment every second. So you can do it on and on, then you can improve the quality of control in this way. So the earliest application of learning control is based on genetic algorithm, and later on, a lot of different kind of like evolutionary algorithm, grading algorithm, a lot of new algorithms can be applied. So by the year of 2010, Professor Ravis had a review paper on New Journal of Physics. They summarized the successful experiments and successful numerical simulation in the literature. By 2010, there are over nearly 200 successful experiments, okay? And there are much more, many more numerical simulation in the literature. So that shows that the learning control can be very, very successful. Okay, and another very influential algorithm in quantum control is GRAPE. It's basically a grading algorithm. It's more often used for microwave control or radio frequency control. Because the time scale is much longer, you can shift the pulse in the time domain, piece by piece, to shift the pulse in the piecewise constant form. So therefore, you have a lot of control variables over here. So the problem is how do you choose the amplitude of this variable. So in 2005, Caniggia and a lot of his collaborators proposed that the grading algorithm can be applied to optimize these pulses. So basically, the idea is also the same. The idea is also the gradient is also calculated from the model using the Schrödinger equation or whatever equation for modeling the system. Okay, so let's summarize the way of thinking of these two different algorithms. They're just the two extremes. So for the GRAPE, I would say this is kind of white box learning control. So, I'm sorry. If you take the quantum control system as something into the box, so GRAPE assumes that you know everything inside it, okay? They assume that the model is perfect, and you use the model to design the control. Okay, this is, from the viewpoint of the machine learning, it's kind of supervised learning. That means that you have the model, you get the model from a bunch of data, and you identify the model from the data, and then you use the model to predict or to design your optimal control. Okay. And another way is the iterative learning control in chemical system can be taken as a black box learning. Okay. So because the system is too complicated or you don't have any model, you just assume that you don't know anything inside the box. But you know how to measure, how to get the output or the objective function from the model. Then you use the model, you get the data from this black box on and on. You get the data online, and you can iteratively learn and improve your control performance. So this kind of from the viewpoint of the machine learning, this can be taken as a reinforcement learning. Okay. So this situation, for example, in chemical reaction, can be applied under two situations. One is the model is unavailable. You don't know the model. It's too complicated. One is the model is too you know the model, but the model is too complicated unless you have a quantum computer to simulate it. But I would emphasize in my talk another different situation is that in quantum computation or quantum information processing, there's another situation is that we do have a model, and the model is very good, but the model is just not good enough. Because in quantum computation, when we want to synthesize a quantum gate, we need a very extremely high precision. Even we have a very good model with high precision, but the model may not be good enough. Okay. So for this purpose, so in the literature there are some there are some algorithms or some iterative learning control experiments or algorithms along this way. So for example, in 2014, Martini group had the optimal control, closed loop learning control experiment for quantum gate Tuneup. Okay, The idea is that they firstly optimize the control field. Firstly optimize the control using the GRAPE, standard GRAPE. Okay. So say the fidelity is the 0.984, not high enough. But from then on, they just don't use the model. They just go to the lab and they use the randomized benchmarking to evaluate the fidelity of this field, the fidelity of this control. And then they use the now-the-mean algorithm to iteratively update the field. But during the iteration, they don't use any model of the system because the model is good but not good enough. Okay, so this is actually a model-free optimization, a black box learning. There are some other algorithms in the literature which I would say that they are all black box learning for optimizing for learning control in quantum information processing. This is the earliest proposed by Professor Rabbis in 1992 using genetic algorithm. And later on in 2009, they proposed another algorithm using gradient. But the gradient is not obtained, is not calculated from the model. The gradient is measured from the experimental data. Basically, they just if you want to calculate the gradient of some control field, you just randomly sample the measurement result along near this control, and you just kind of interpolate the gradient direction from this data. So in that case, they use the gradient, but the gradient is not calculated from the model. And there are some other algorithms using now-the-mean. It's kind of a simplex algorithm, deterministic, but model-free algorithm. Okay. And also there are some other gradient algorithm. This is a stochastic gradient algorithm. This is a gradient algorithm. These two ideas is very similar to this one. They just obtain measure the gradient from the experimental data. So let's look at the whole process of the learning. So basically, for quantum information processing, if you want to have a very high precision gate, you firstly use the model. You first identify a model, and you use the model to in an open loop way to design the optimal control. Okay, so model-based power design. Okay, then you get a good control over here. But this is not your final pulse, because the pulse is not the precision is not high enough. So this pulse is only used for an initial guess for the following iterative learning. Okay. Then in the following iterative learning, closed loop iterative learning, they just use the measurement data. You measure the system and apply the pulse to the system, and then measure again, and then use the result to update your field, and on and on and on. You can get a good, very good solution. Okay. So this is the case. Okay. So this is actually a two-stage optimization. In the first stage, you use the model to get a good but not good enough control, and then then in the following optimization, people actually does not trust the model. They only trust the data. They only use the data to optimize the field. Okay. So this is my question too. So in this closed loop learning, what to use or not to use the model? So this question has haunted me for a long while, because the model we do have a model, and the model is often very good. But why don't we use the model in the iterative learning? So there are a lot of information, a lot of knowledge in the model. So this is from the ideas of our recent research. Is that our conclusion is that even the model is not good enough, you can still actively use the model in the closed loop learning to get a good solution. Okay. So here are the two examples. Okay. The first example is we apply the iterative learning to get the modified version of deconvolution to an iterative deconvolution. The I represents the iterative. Okay. So this problem comes from my discussion with my collaborator on the superconducting experiment. In their experiment, if you have a quantum chip, so in the refrigerator, say, okay, and you often apply a microwave field here to control your chip, the qubit, and you measure the signal and give it to the say FPGA to do the optimization. So it often happens that okay, say you want to generate a Gaussian signal over here in situ signal, but the problem is when you generate the signal from in the room temperature, then firstly when you tell the AWG arbitrary waveform generator, it will firstly discretize the pulse. Okay. Then when the pulse goes down from the room temperature to the low temperature, it will experience a different kind of distortion. Say, because there are spurious capacitors and inductances along this transmission line, they can experience the linear distortion. Okay, the change, the shape. There could be also some nonlinear distortion. So when this signal comes from a long way from the AWG, from the transmission line, goes here, the pulse shape will be distorted. Okay. So here's the iterative learning can be useful. So in the experiment, I learned this idea from the Yale group. You can find this deconvolution idea from this PhD thesis. So their idea is very simple. They just use a compensation. Okay. So firstly, they say this is the input of the AWG, and this is the in situ signal. So firstly, we can just build up the model. Say the model is represented by a transfer function, GS. So that's the model. So from this AWG signal to this in situ signal, so there's a convolutionally distortion. Okay. So now, if you know the model, you can just put the inverse model of this one just in front of this reference input. Okay. Then I want to generate some signal, say UD. You can put it here and here. And this signal is just, if you apply this signal to your AWG, then the output will be exactly the desired signal, because the inverse composes the model. It's just identity, right? So this idea is very simple. I think it is applied in many ways. But the problem is that in practice, you have to identify a model from the experimental data. The model is often not accurate. Okay. And also another shortcoming of this method is that you assume that the model is linear. But in practice, there could be nonlinear. In practice, there could be nonlinearity in the model. So there's some limitation of the deconvolution. Okay. Okay. So we can say this way. Okay. If your real dynamic is represented by this GS transfer function, but when you apply this deconvolution using this inverse model, but then the model is not good enough. It is not exactly the real model. Then the output will not be exactly what you want. Okay. So our idea is that, okay, you have a model but not good enough. But you can use the model in an iterative learning way to gradually improve this AWG signal to make it better and better. So the way we do it is that, okay, so when you firstly apply this field, apply an initial guess, you can use any initial guess field. Then you can measure the error signal. Okay, the real signal and the design signal, you can measure the difference. Okay, then you use the difference and apply this reference model. This model is what you apply here. This model may not be good, and may not be accurate, but it's good but not good enough. Okay. Then you use this. Then you use the error signal and you use the reference model, and you can update your reference signal, and on and on and on. You can easily prove that the error signal follow this relation. So the error signal and the next error signal, the relation between them is like this. So if you properly choose a learning rate, basically the learning rate, you can make the operator norm of this transfer function be smaller than 1. So in this way, you can gradually, the error will decay using a proper learning rate. Okay, this is some simulation result. Okay, so firstly, if you apply a, say I want to generate a step signal, in situ step signal, which is often required in simple conducting quantum computation. So if you choose the initial field step function, then what you see in situ the quantum qubit is like this, being distorted, because there is some delay component along the transmission line. Okay, I use a model for this. This is just a linear model. Okay, so now, okay, I want to correct this distortion. Okay, and then now use a reference model. So assume I don't know the real model. So the model I use is like this. It's different from the real model. But the model is not much different. Okay, it's only slightly different from this. Then you use this model to correct it. The first iteration, you correct the signal like this. And on, you can correct the signal like this. Like this. There's something over here. I will explain it later. Well, this you use a good model. Okay. But the method is very, it's kind of very robust, because even if you use a very bad model, you see the model is, well, it's very different from the real model. I applied the bad model here. So also during the iterative correction, the shape of the corrected shape is different from here. But finally, if you take more and more, if you take more iteration, finally you can get the same result. Okay. So that means that the final result is independent with the reference model, whatever good or bad model, as long as the model is not too bad. It could be a little bad, but not too bad. Okay. So this is the iteration learning process of this pulse. This is the error signal. This is the in situ signal. You can see initially it climbs very slowly, but more and more, it's much closer to the desired signal. But we want an ideal step signal. But why do we see here? Something here. This is very straight, right? So this actually comes from the sampling. Because when we use the AWG signal, we generate the signal with finite sampling rate. Okay. So if we change the sampling rate of the AWG signal, we see that the behavior here changed. If we use longer sampling period, the overshoot will be lower, and there is fewer oscillation over here. Okay. So this shows that the iterative deconvolution could work. Okay. But sometimes you have to be careful, because if you happen to use some kind of model which we call non-minimum phase model, this is what we call in classical control engineering. Non-minimum phase means that if your transfer function has some poles or some zeros in the in the right hand of the complex planes, right? So meaning that the pole or the zero are unstable. If you have this kind of reference model, then you have to be careful. For example, if we use the model for the iterative learning control, you can see the way initially it can oscillate very violently. But fortunately for this model is bad, but not too bad. So on and on, it takes more iteration. The iterative deconvolution will pull this correction back to this ideal to this signal, the same signal. But if you use even worse, if you use if you use a model worse than this, then the iterative will diverge. Okay, the iterative learning will be unstable. Okay. Now let's see how this happened. Okay. So this error actually comes from the finite sampling of this measurement or the AWG signal. say I want to generate a step function like this way. But the problem is that I can only measure this and measure my result only at a finite sampling time. I can only see whether my correction is good or bad only at this sampling time. Between this sampling time, I can see nothing. Okay, if you only focus on this sampling time, you have no control of this the pulse behavior between the sampling time. So, say I want to correct the signal to the ideal step signal. I need the AW pulse to just push this in situ signal just exactly across this value 1 here. Then after that, because the model dynamics is linear, because linear dynamics always have inertial. Okay, because of the inertial dynamics, the curve will keep going up, but the correction will put the curve back to this pull back this curve back to this step function at the next sampling time. So on and on, push it up and back, push it up and back, you have this oscillation. So this is intersampling behavior. Okay, so therefore the intersampling behavior is comes from the finite sampling rate. Okay, so if you look at the error signal, we can evaluate the correction performance in two ways. One way is we only look at the error at its sampling time over here, but I think the real error between the curve and the step function is the continuous, the areas enclosed by this step signal and this continuous signal. Okay, but you can see that the error is very different. If you only look at the sampling errors, you can just monotonically decrease it to arbitrary precision. Okay, but if you look at the continuous curve error, you can see firstly it decreased, and then it will slightly rise up. Okay, in machine learning, this kind of overfitting. If you only focus on the data you are training your model, you will not get the best model. Okay, so the best performance actually is achieved around the 5th or 10th iteration. Okay. Okay, so this is intersampling behavior. Here I show some example showing that this intersampling behavior is due to the linear dynamics of this transmission line. But if you can actively add some nonlinearity in the transmission line, you can kind of suppress this oscillation. If you have some nonlinearity inside the system, you can make the shape much better. Okay, I will say too much on this. Okay, then the second example, from GRAPE to d-GRAPE. This paper can be published this year. So let's firstly look at the graded algorithm we use in practice. So say we want to control a gate, okay? And we use the graded, we calculate the graded. If we calculate the graded in continuous time, the graded formula is like this, okay? But since we are doing the optimization in discrete time in piecewise constant field, so in practice the gradient formula is actually a approximate one. It's accurate when the time period is very small, when delta t is very small. Okay, but when you look at this, this gradient formula is a little different from the original formula in this paper. Writing in this way is that you can see from this gradient formula, you can divide it into two parts. One part is only related to the final state propagator, okay, only related to the final time. And the other part is related to the whole trajectory, whole evolution trajectory. So the real grade, so in practice we can do the real grade. If we follow the real gradient, we'll do a very precise gate, okay? But in practice, we don't have a good model. We don't have the precise model. We have only a design model, which is not exactly the same as the real model. So in practice, we can only follow a different way. And in the end, what we achieve is different from it. But we can be close. We can be close. So now the problem is, how do we get from here to here? Okay. So the way the people are optimizing the field from here to here is using some stochastic algorithm or some model-free algorithm. It could take a long way. But my idea is that, okay, you have the ideal gradient, but you are not able to get it because you don't have the model. But you can calculate the gradient from your design model, but this gradient is not precise. But you can combine them together. Okay? You can use this part from the real model, and you can use this part from the design model. And this part from the real model, you can obtain it by tomography. You can measure it, because it's only related to the final time propagator. You can just measure it, for example, using tomography. And this part, you can just use the model to calculate it. Okay? So in this way, you can find a approximate gradient path from here to here. Okay. So the basic idea is that, okay, so my system has some kind of distortion, a lot of model uncertainty, but I can do tomography. When I use gradient algorithm, one part I use tomography to get the error signal, and one part I use a design model to get another component used for the gradient estimation. Then I get a gradient estimation, use it for iterative learning. Okay. And the result is that, okay, here is the example. The example here is, okay, I have the uncertainty parameter here. See, this is a two-qubit system. Okay, I have 4 control fields here. And I assume that I don't know this coupling constant exactly. In the design model, the coupling constant is J, but in practice, but in reality, the coupling constant has some uncertainty here. And also, I have pulse distortion over here. Okay, you can see that if you follow the ideal gradient path, you can optimize to arbitrary precision down to the machine precision. Okay, this is ideal, but in practice, you're not able to do that because you don't know the model. But if you follow the gradient I defined previously, you can gradually optimize, improve the performance to reduce the error. But here is to some finite precision. The precision is that because you have to use your tomography, but the tomography has some precision. So the final performance is limited by the tomography error. So as long as you can do very high precision tomography, you can optimize your field up to that precision. Okay. And you can also say if you use a good model, and most optimization will iterate a little slowly than the ideal gradient path, but not so much. But if you use a worse model, well, sometimes, okay, it can be much more slowly, and sometimes it could just go away. So, but in practice, you should have a good model like this. You have here I assume that the uncertainty is like 5%, and the rising time is like a tenth of this sampling period. Okay. So this is what I can show you that this gradient algorithm can work. And to compare this algorithm to other learning algorithm, so it's very hard it's kind of not easy to compare because, for example, if you compare this algorithm with the Nonlinearity algorithm using randomized benchmarking, it's kind of hard to compare because if you use the d-GRAPE, you can have fewer iterations. But the problem is that tomography might be more expensive than randomized benchmarking. But if you use randomized benchmarking, it can be easier to do the benchmarking, but you may need a lot more iteration. But one thing I can compare, I'm not going to compare the total efforts which equal to the experiment effort every iteration times the total number of iterations. I will not compare this. But I can show you that when you use the pulse, when you increase the pulse number, so you discretize the pulse into 10 pieces, into 20 pieces, into 50 pieces. So when you increase the number of the control variables, the number of iterations, when you change from 20 to 50, the number of iterations using d-GRAPE will be smaller, will be faster. But when you increase the number of the pieces, the number of iterations for using randomized benchmarking will be much greater. So it will be slower. Okay. So d-GRAPE can be more efficient when using a pulse that includes a large number of pulses. In this way, it can be very efficient. And the effort does not increase with the number of the pulses because what you do is only you need to do the tomography. And the effort is not related to the number of pulses. Okay. Finally, the conclusion. So the result is that first, so the idea behind is that we should make best use of both model and data, not just use model, not just use data. Right. Second, we should make best use of graded because we have a very nice landscape. We should make best use of graded. And the limitation. So this grading algorithm works great for deterministic or systematic errors, but for random errors, stochastic errors, so this is not what it's good at. So dynamical decoupling will be, I think this should be handled by dynamical decoupling. Right. So finally, beyond d-GRAPE, so this just shows you that you can do more with the grading algorithm using online data. So for example, if you want to find you have many solutions, but some solution is robust, right, the flat. But some solution is not so good, sharp. If you want to find this one, but not this one, but you can have some other design. So for example, we have some what we call A-GRAPE, B-GRAPE. We can also have C-GRAPE, medi-GRAPE. So we can have some more wisdom from the machine learning, from many learning wisdom. That's the end of my talk. Thank you.
So we have quite a bit of time for discussion, so I invite you to, if you have any questions.
Oh.
Can you go back to your very beginning sort of diagram of the fridge and everything?
Which one?
Like the picture of the fridge, like towards the beginning.
4.
Yeah. Like you're setting this, the one where you set the stage is like slide 2 or 3.
Which one?
Yeah, like here. Yeah.
Okay.
So like what I took from especially the first part of your talk was it was sort of as if one had, so at the end of the second attenuator, you sort of tap in there and you measure the pulse that's being delivered to the DUT.
Right.
And an experimentalist does this all the time, and that's how they help sort of tune that right till you get to the DUT.
Right.
Now the hard part comes, and so that's often very linear transformation. Hard part comes when it goes to the DUT. And if it's something like a qubit, it will sort of act as the sinusoid times the integral of that pulse, which is a nonlinear transformation.
Okay.
And so I liked your theory of how to iteratively correct for linear transformations. But the hard part of these sorts of experiments is the nonlinear transformations, basically like a sinusoid times the on the integral of the pulse, inverting that and then trying to tune up the pulses.
Oh, yeah. But the theory here is that even if you have nonlinearity, but if the nonlinearity is not so strong, you can use the iterative learning.
But the point is that it is very strong because the sinusoid. Yeah.
well, but in that way you can. Well, that depends on the model. But you can incorporate the nonlinearity using the model. But you can use the model. You can put the nonlinearity into this reference model.
But the point is that the G there is
you can
very
make it
far
nonlinear.
from.
You can make it nonlinear.
It's extremely nonlinear.
No, it could. Yeah, it could be. So this is just basically, it is easy to interpret this idea using a linear model. But it can be absolutely extended to generalize to
so, but it's also a nonlinear model that doesn't have a one-to-one.
One-to-one.
Because it's a sinusoid. It's a sine times an integral. So you don't know how many wrappings has happened.
Well, that would be very
necessarily.
interesting.
So just if you could solve that problem, that would be very interesting to see.
Oh, thank you very much. Yeah, I was thinking about that.
Two little questions. So, number one is when you have these approaches to d-GRAPE, where you really invoke the learning about the model, and you deduce the gradients from there. Is it possible also to incorporate that into second-order methods? So probably this should be, because the current state of GRAPE, of course, is that it really absorbs some quasi-Newton methods to really faster converge. And therefore the question is whether from the gradient you calculate, it should also be possible to approximate something like an inverse Hessian. And I think by LBFGS type of approaches, this should be possible.
In principle, you can do anything. Using second order, you can do anything.
Okay. The more important question is the second now, and that is, you mentioned also the paper by Eggert and Wilhelm, the ad hoc method. And I think one of the very nice take-home messages from that paper is that if you start with a closed-loop feedback control, Nelder-Mead, too early, then you end up in bad fidelities. And you have to know somehow a sweet spot of switching methods from gradient, from initial gradient enhanced methods to the more refined ones. Does this also hold for your d-GRAPE approach? So do you know something like a sweet spot when to really go for the full Monty that you introduced to us?
Well, this is an interesting point, but to be honest, I don't really look at it into this.
I think this would be really a very important point for making the most out of your very nice approach.
In my simulation, I just use the design model to do the optimization to get a solution as good as possible, and I just start from that to use to make it online. So I didn't really look at the turning point issue, but that would be very interesting and important.
Thanks, Rebing, for a very nice talk. Also about the deconvolution aspect of your work. It looked like the way you were doing the simulations and the iterations was to calculate the effective distorted waveform and then kind of match to what you were targeting. But as we were hearing before, it's only partially possible to do that. And in general, when you get to the qubit on a chip or in some other setting, you only have access to some indirect proxy measure of the quality of your pulse. It's difficult to have a non-distorting tap that brings your signal back up. So have you thought about alternative measurement strategies, not just using randomized benchmarking and reducing to fidelity, but some other protocol that allows you to get more information about the distortion itself?
Well, so actually I know this issue from my discussion with the experimental guy, but I just assume that we can perfectly measure the distortion, but how to identify the distortion is very important. Probably we can have some system identification theory or methods from the classical control engineering. I think that should be useful, but I haven't looked into this.
Maybe we can talk some more.
Maybe we can, yeah, sure.
So we still have a bit of time. Any more questions that?
Maybe a more very technical question. The fact that you have some oscillation, in fact, when you have
for the deconvolution.
In the deconvolution schemes comes maybe from the fact that you want to have a step function at the end of the attenuation scheme, and it is not possible because it is a low-pass filter. So the output of a low-pulse filter cannot be the step function, which explains this kind of overshoot and so on. Maybe. Is it related to that? Because you want to have a step function at the end. And it's impossible to have a step function as the output of a first-order filter.
Yeah, it could be possible if you
Maybe
don't
to smooth a little bit, will remove this kind of oscillation, I guess.
Yeah. So the challenge here, if the most difficult thing to calibrate the pulse is for this kind of very sharply training pulses.
Yes.
For smooth pulses, it's much easier.
Yes.
Yeah.
If you take, for example, a Gaussian in this
yeah,
case,
the Gaussian is much easier. It's much easier.
Much
I tried. Yeah, I did do this simulation, but
yes.
it's much easier. So.
Yes. Because it seems to me that it is not possible to have such kind of things.
Right. It's not possible because So for the linear dynamic, for the inertial
output signal is continuous at least.
Right. Yeah.
We do see this. We see this in experiment all the time.
All the time, right?
You see when you make square pulses in any microwave experiment that it's not the roll off from RC or something. It's this kind of sampling error that gives you oscillations.
We also think that in electroengineering, there is a lot of wisdom of these transfer functions, and they are classified and modeled, so one also doesn't have to start from zero. They really do have all this wisdom.
Right. Yeah. Okay.
More questions? No, if there are no questions, so let us thank Rebing once again. And
okay, thank you.